Hello everyone and welcome back to the channel. In this video, we will analyze a shellcode loader. We will use the Ghidra scripting that we've learned in the previous video to create a script which will add comments to the Ghidra project. We will then extract the shellcode from that project and use the Flare VM utilities to analyze the shellcode as well. With that, let's dive in. So here I am in my virtual machine. I will open up Ghidra first. In Ghidra, I will create a new project. And in this project, I will drag and drop this runme.exe. Okay. Press OK here. Now I will click on this. This will open up the file in the Code Explorer. Yes. Analyze. And now the file is being analyzed. The analysis is now complete and we are at the startup function. This is actually the main function. Inside it, you see that this is something else. This is just the initialization, but the actual main function here is the startup function. This contains another function which is called thread exec. Let's go into that. And if we go into thread exec, let's go line by line. It's a very short function and this is a very short code, so we can go line by line and analyze it quickly. So the first thing that we see here is PAU-var2 and something is being extracted from this function, get function address by hash, and it is being returned and assigned to PAU-var2. And after that, PAU-var2 is going to be called over here, and this is being passed something like 0. Okay. After that, there is a printf statement, could not allocate memory for payload. And then we have a couple of more get function by hash, and this one is msvcrt.dll is being passed and another hash is being passed here, then kernel 32, then another hash. Okay, so this is going to be a bit more difficult if you're not able to analyze what this function does. Now, with my experience of looking at malware, I can already see that this is part of dynamic API resolution. And if we look at this hash and if we Google this, we will Google this and we will find that this comes up in this article, reflective DLL injection in the wild. And if I go to this article, I will find that by the same ROR13 hash method, the loader is trying to locate 6 specific functions in kernel 32. Virtual alloc is this one, 091AFCA54, which is this one. Then we have MSVCRT. This is not in the article. The next one is 85B. 85B is also not there in this article. Then we have 61B. 61B is there in this article, which is virtual protect. So this one is virtual protect. 06B. 06B is also not there. And 9AD. This is also not there. All right. So we now have at least an indication that this is a ROR13 hash method. And if we go inside this function, we can see some more details. Let's go down. And this is the part which is going to be interesting for us, this do while loop. Inside this, we can see that there is a right shift operation going on, and this is shifting it right by 0xd, which is decimal 13. So this is the giveaway which shows that this is ROR13. Now, what we want to do is We want to find out what are these other APIs, and then how can we make it easy for us to analyze this code further to understand what is going on. So the first step is going to be to extract the hashes and the APIs linked to them. So for that, I have written up some code. Let me open up Visual Studio Code. And inside Visual Studio Code, there is a file called generatehashes.py. Now in generatehashes.py, let me just make it a bit smaller so we can see it clearly. In generatehashes.py, what I've done is I've written a method called ROR here. And then I've written another function which generates the hash. Now this hash function calls the ROR function, and it passes in these bits, which indicates that we are doing ROR 13. And after that, I have created two arrays here, interesting DLLs and interesting DLLs 1. Now we are going to perform our operation on interesting DLL1 because we know that only kernel32.dll and msvcrt.dll are being used inside the code that we are analyzing. We can see it here clearly, right? That msvcrt is being used and kernel32 is being used. But if we have an indication that all of these DLLs are being used, then we can pick and choose whatever we want and put it here, and the hashes along with the API names will be generated for those. For now, I want to save time and I've only generated it for these two DLLs. Now if we go inside the main function or the main loop, we see that for file name in system32, if the file name is in interesting DLLs, which means if the file name is kernel32 and msvcrt32, then we open up the P file, we look for all the exports inside the P file, and for each API name we convert this into UTF-8, and after that we generate the hash for that API name. Then what we do is that we have a dictionary over here, export list dictionary, and inside this we add the hash along with the API name to create a dictionary with the API hash as the key. This will make searching easier for us. So I want to do one round of debug so you're able to see what is going on here. So let's put a breakpoint here for file name in OS list directory. So debug this Python file. I'll close this below console, which is not needed anymore. And let's go step by step. So let me put here file name. See, it's going over all the file names. I don't want to go over this part of the loop, so that's fine. Let me close this and let me go here. And now it is hitting kernel32. So we are where we need to be. For export in the kernel32 DLL, we extract the API name, and the first API name that we have is acquire srw lock exclusive. And for that API name, we have the hash generated by calling this function and then creating a hex, a decimal value for it. After that, we add it into the export list. If we see the export list right now, we'll see the first value getting added here. And the first value, the key is the API hash, and the value is the API name. Okay, we can see this. All right, so this operation will keep on continuing, and after all this is done for both the kernel32 and msvcrt.dll, it is going to dump this in the exports.json file. Now I've already done that operation before, and I've created an exports.json file, which we can see here. We see that all of these values, hashes, have API names over here. Okay, hash and then API name. Now let's see if we are able to find out the hashes which are there in this code inside that hashes.json file. So we can find the first hash, which is virtual alloc. The second hash is printf. We can see this colon printf. And then next one is RTL move memory. So we can safely say that all the hashes that are there in the code are already there in the exports.json file. Let's go back. Now we need to find a way to label all these places. 1, 2, 3, 4, 5, 6. Now, usually I'm able to do these 6 values by hand and add comments over here by hand, but I want to show an example of how we can do it for a lot of these functions. Let's suppose that there are 50 of them. Now it's going to be a pain that we extract one hash from here, then go to the exports.json file, look for the hash, then come back here and add the comment. So for these kind of repeated operations, I would like to write some sort of a script to make it easier for me to analyze this code. And since we've discussed the Ghidra scripting using the Ghidrathon Python extension in the last video, I'm going to do that. So I've written a script over here and we can discuss the script now. So what is happening in the script is there are a couple of functions. The first function is read JSON file. We already know what this is going to do. This is going to read the exports.json file. Find move instruction. This I will tell you when I will go over the main code. And in the main code, what is happening is the file path is being opened, which is the exports.json, and we are reading the JSON file. Now we are looking for the get function address by hash. Okay, that's fine. And then we are getting all the global functions and we are looking for that function name. Okay. And for item in the function, so in a function there can be multiple values, and in that case, in this case, we are looking for the entry point. Okay. Now after that, we are trying to get the references to that address, which means that this is the entry point over here, 14001800. And basically what we are trying to find out is this list. We are trying to get the references. So this list will come back to us. Okay, this is going to be returned from here, references. And for each reference in the references, we are saying that if the reference type is an unconditional call. Okay, so there can be multiple type of references and there can be a data type of reference as well. We've seen this in the last video. So we are trying to find out if this is an unconditional call. And if this is an unconditional call, so we can see that we extract the reference at the address, and reference.get from address will tell us where is this call from. So if we only run this code, put it here, we'd see that as part of this printing, we can see that reference at address 164E, which is here, 1681, 169A, 16BA, 16F0, and 1700. So we have a good list of all the places where this function is called from. And then we get the caller address and we assign this from this function which we saw here, the same thing. So the caller address list is going to contain all these addresses, and the caller instruction, let's look at that. So we can take this piece of code and execute this in Ghidra. I'll paste it here and we should see the from address, which is here, and the mnemonic string is here as well. Okay, so for each address we see 140016F0. This is a mnemonic string, which is a call instruction. So it's fine. We want that exactly. And after that, we want to find the move instruction. Let's analyze the find move instruction. This is fairly simple to analyze. Once we have found this call instruction over here, what we want is to extract the hash, this hash. So we have got this call instruction here and we want to extract this hash. And how can we do that? So we will go line by line backwards and we will look for this move instruction. Once we find this move instruction, we will look for EDX. So EDX is going to be operand 0 and this is going to be operand 1. Once we find the operand 0 as EDX, we are going to extract this operand 1 and this is going to be our hash. Now, how do I say this is going to be passed in EDX? Because if we look at this call, we see that the first argument is kernel32.dll. The first argument is always passed in the ECX or the RCX register, and the second argument is always passed in the EDX or the RDX register. In this case, we see it's passed in the EDX register, and so this is going to be the hash that we want. Now let's look at the code. Find move instruction, go to definition. So if we look at this function, we see that an instruction has been passed and an API hashing dictionary has been passed. All right. So this instruction is the call instruction. So what will happen is, as we discussed before, we are going to get the previous instruction, and from the previous instruction we are going to get the mnemonic string, and if the mnemonic string is a move, then we are going to go inside this condition, and inside this condition we're seeing if the operand 0 is EDX, then we basically extract the operand 2 and we print this and we assign this into API hash as well. All right. After that, we look for this API hash in our API hash dictionary, and then we print out the API value as well. Okay. So let's suppose that after this function has executed, we get the API. What happens next? So after we get the API from here, we say colon instruction dot set comment. Colon instruction is this instruction, which is going to be this instruction here and this instruction here. We say colon instruction dot set comment. On the colon instruction, we want to set an end of the line comment, and we want to say that the comment will be the API. So let's suppose that for the first time this function is executed, we send it this API hash, we get the value returned of virtual alloc, and after virtual alloc is returned, we basically set it as a comment on this line and this line. So let's see that in action. I will copy the functions first. Let me copy this and put it there. It's fine. This is ready. Now, why I'm doing this step by step and extracting each function and pasting it there is because sometimes the Ghidra or Ghidrathon does not like the big pieces of code being pasted inside. So this is why I'm doing this. Next up, let's take this, Control C and Control V here. Now let's go over the extract. So a reference is at address 140000164E. We see that this is a call instruction. The mnemonic was found as move. The address is 140014646, which is this one. And we see that this is RSP0x3C. So that's fine. Then we have a move instruction, which is address 1643, which is this one. And in this one, the operand 1 is RCX, We don't want that. Then we look for the next one, which is the move instruction, and the address is 1400016 which is this one. And from there we want the first operand, which is edx, and the second operand is 091afca54, which is the hash. We have gotten the hash, and now we found out that the API is virtual alloc. Now what happens after the API of virtual alloc is extracted? We see that there is a comment added here which says that this is virtual alloc. We see that the comment for virtual alloc is added over here, but it's not added over here. Now, how can we do that? Let's look for the set and let's see what kind of comment shows up here. So sometimes what will happen is that in Ghidra, all of the different types of comments will not show up in the decompiler part of the code. So therefore, we'll have to make sure that we set up the right kind of comment. So let's go here, set plate comment, and end of the line comment is already there. Pre-comment. Let's set a plate comment and see if that works. We saw that plate comment did not come here. Let me remove this. Apply. Let me put a pre-comment. So pre-comment is coming over here. That's fine. Let me remove this. Apply. Okay. And let's do a Control Z. So let's put a pre-comment here. It's fine. Control S. And let's execute this part of the code again. Okay, now we see that virtual alloc comment has been added here and the virtual alloc comment has been added here. If we start going down, we can see that this one is printf, this one is RTL move memory, this one is virtual protect, this one is create thread, and this is the wait for single object. So we see that this is the basic flow for executing a shellcode. And if you look closely over here, there is this RTL move memory. Firstly, there is virtual alloc over here. And virtual alloc is being basically called here, and lvar3 is getting the address of the allocated memory. Now we see over here that RTL move memory is being called, and lvar3 is getting some value inside it, and this is the value from which comes from here, data section. And if we convert this to code, disassemble, we see that this is actually shellcode, and we can see the disassembled part or the decompiler part of the code over here as well. So we want to analyze this shellcode, and for that I have written another script, Python script. So let's go and look at that. Extract the shellcode. We see that the shellcode is starting from 140000800. This Python script is starting from this address, and it's taking the length of 0x11b. Where does this come from? Let's go back. This comes from this payload length. If we go to this payload length, we will see that 0x11b is extracted from here. We have an output file which is going to be the shellcode.bin, and basically what we are doing is we're getting byte by byte from the current address, and the current address is being moved to the next bit. And after everything is done here, we basically write all this data into the output file. Okay, so let's copy this and let's paste it here. This should give us the shellcode in the shellcode.bin file, fc, and then we have h, which is going to be the character for 48. Then we have 83, then we have e4, then we have f0, e8. All this data has been extracted and dumped into the shellcode.bin file. Now we are going to use a utility called speakeasy to basically understand what this code is doing. So let's go to our Ghidra scripting folder, open up our terminal, and we will use speakeasy to analyze shellcode.bin. So the way speakeasy works is, let's look at the help first. So speakeasy -t will give you the target. Okay. And then -a will give you the architecture, and -r tells it to run it in raw mode because this is shellcode, right? So that is what we are going to do. Let's use speakeasy again. Speakeasy -t ./shellcode.bin -r -a, and -a for 64-bit we have to write AMD64. AMD64, press enter, and we see the shellcode is basically running calc.exe, and after that it gets the version and then it stops. It stops because it is waiting for the thread to exit. It does not matter here. The only thing that matters here is the execution of calc.exe. So I think we now have a good understanding and overview of how we can use Ghidra scripting to analyze a piece of code. We are able to add comments via that. We are able to extract function or call parameters via that as well. And then finally, we were able to write another script to extract the shellcode and use a third-party utility to analyze that shellcode as well. With that, thank you very much for your time, and I'll see you in the next video.